Okay, uh, now let's continue. Field mice and owls. Now let us look at another quite different example. Consider a population of field mice that inhabit a certain rural area. In the absence of predators, we assume that the mouse population increases at a rate proportional to the current population. This assumption is not a well-established physical law, as Newton's law of motion is in example 1, but it is a common initial hypothesis. A better model of population growth is discussed in section 2.5 later. In a study of population growth, if we denote time by t and the mouse population at time t by p of t, then the assumption about population growth can be expressed by the equation. Let's write down this equation. dp over dt is equal to r times p. This is the seventh equation. Where the, the proportionality factor r is called the rate constant or growth constant. This r and p is the population. To be specific, suppose that time is measured in months and that the rate constant r has the value 0.5 per month. Then the two terms in equation then the two then the two terms in equation 7 have the units of mice per month. Now let us add to the problem by supposing that several owls live in the same neighborhood and that they kill 15 field mice per day. To incorporate this information into the model, we must add another term to the differential equation 7 so that it becomes let's write down this equation so that it becomes dp over dt is equal to p over 2 minus 450. This is the equation A. Observe that the predation term is minus 450 rather than minus 15 because time is measured in months. So the monthly predation rate is needed. So maybe now let's figure out what's happening here. To be specific, suppose that time is measured in months and that the rate constant r has the value 0.5 per month. So now t is in month, month, and r has the value 0.5 per month. Now let us add to the problem by supposing that several owls live in and they kill 15 field mice per day. So they kill 15 mice. Kill 15 mice 1 day, days per day. And we want to align the units. Namely, we want to use the unit of month, not day. So we want to know what is a month and how many mice. And a month is equal to, let's say, is equal to 30 days average. So 15 mice 1 day. So what is corresponding to 30 days? That is 15 times 30, and this is 450. This mice corresponding to a month. And we substituted the value of R to here. So we can get 0.5 times P here. And this is P over 2. And then we minus the 450 mice per month. And lastly, we get this result here. Example 3. Investigate the solutions of differential equation 8 graphically. This is the specific differential equation for this example, for this problem. Solution, a direction field for equation 8. Let's narrow down this window. A direction field for equation A is shown in figure 1.1.4. For sufficiently large values of P, it can be seen from the figure. The vertical axis is P axis. The horizontal axis is T axis. For sufficiently large values of P, it can be seen from the figure or directly from equation 8 itself. The dP over dt is positive. Let's see this equation if P is very, very large, and this whole result is a positive value. So the solutions increase. Solutions is P's of T is increasing as T increase. You can see this. On the other hand, if P is small, then dP over dt is negative and solutions decrease. Let's see if P is small. Let's see, maybe it's 1. So this 1 over 2 minus 450 is negative. So this is negative. And then the P of T is decreasing as T increase. Again, the critical value of P that separates solutions that increase from those that increase from those that decrease is the value of P for which dP over dt is 0. By setting dP over dt equal to 0 in equation A, then solving for P, we find equilibrium solution. P of T is equal to 900. Let's do this calculation. So let this term equal to 0 and P minus 450 and we can get P is equal to, let's move this term on the left and then multiply by 2, we can get 150 multiplied by 2 and it's 900, for which the growth term and the predation term in equation A are exactly balanced. And this is, the left term is a growth term because the population is grow, and the second term is a predation term because the owl eats the mice. In this situation, because it's zero, so these two terms, they are balanced. The equilibrium solution is also shown in figure 1.4, and this line is where P is equal to 900. Comparing examples 2 and 3, we know that in both cases, the equilibrium solution separates increasing from decreasing solutions. We can look at this increasing, this is decreasing. Example 2, other solutions converge to or are attracted by the equilibrium solution, so that after the object falls long enough, an observer will see it moving at very nearly the equilibrium velocity. Let's look at that figure. This is for example 2. That's right here. This is example 2. It's converging. On the other hand, in example 3, and this is example 3, other solutions diverge from or are repelled by the equilibrium solution. Solutions behave very differently depending on whether they start above or below the equilibrium solution. As time passes, an observer might see populations either much larger, for example, in this situation, it becomes larger, or much smaller, for example, in this situation, becomes smaller than the equilibrium population. But the equilibrium solution itself will not, in practice, be observed. This. In both problems, however, the equilibrium solution is very important in understanding how solutions of the given differential equation behave. A more general version of equation A is, let's write down this equation. Let's write down this equation. dP over dt is equal to R times P minus K. This is equation 9. A more general version of equation A is equation 9, where the growth rate R and the predation rate K are positive constants that are otherwise unspecified. Solutions of this more general equation are very similar to those of equation 8. The equilibrium solution of equation 9 is P of t equal to K over R. Let's do it simply. Let this dp over dt be 0. Then we get r times p minus k. Then we get p is equal to k over r for r, the positive numbers are positive constants. Solutions above the equilibrium solution increase, while those below it decrease. You should keep in mind that both of the models discussed in this section have their limitations. The model 5 of the falling object is valid only as long as the object is falling freely without encountering any obstacles. Let's look at the equation 5. This is the equation 5. If the velocity is large enough, the assumption that the frictional resistance is linearly proportional to the velocity has to be replaced with a nonlinear approximation. The population model 8 this eventually predicts negative numbers of mice. If p is less than 900, this is negative, or enormously large numbers if p is very, very large. Both of these predictions are unrealistic, so this model becomes unacceptable after a fairly short time interval. Next, constructing mathematical models in applying differential equations to any of the numerous fields in which they are useful. It is necessary first to formulate the appropriate differential equation that describes or models the problem being investigated. In this section, we have looked at two examples of this modeling process, one drawn from physics and the other from ecology. In constructing future mathematical models yourself, you should recognize that each problem is different and that successful modeling cannot be reduced to the observance of a set of prescribed rules. Indeed, constructing a satisfactory model is sometimes the most difficult part of the problem. Nevertheless, it may be helpful to list some steps that are often part of the process. 1. Identify the independent and dependent variables and assign letters to represent them. Often the independent variable is time, or t. 2. Choose the units of measurement for each variable. In a sense, the choice of units is arbitrary, but some choices may be much more convenient than others. For example, we chose to measure time in seconds for the falling object problem and in months for the population problem. 3. Articulate the basic principle that underlies or governs the problem you are investigating. This may be a widely recognized physical law, such as Newton's law of motion, or it may be a more speculative assumption that may be based on your own experience or observations. In any case, this step is likely not to be a purely mathematical one, but will require you to be familiar with the field in which the problem originates. 4. Express the principle or law in step 3 in terms of the variables you chose in step 1. This may be easier said than done. It may require the introduction of physical constants or parameters such as the drag coefficient in example 1 and determination of appropriate values for them, or it may involve the use of auxiliary or intermediate variables that must then be related to the primary variables. 5. If the units agree, then your equation at least is dimensionally consistent, although it may have other shortcomings that this test does not reveal. 6. In the problems considered here, the result of step 4 is a single differential equation which constitutes the desired mathematical model. Keep in mind, though, that in more complex problems, the resulting mathematical model may be much more complicated, perhaps involving a system of several differential equations, for example.